good evening, and welcome to Cozy Sleep Time. Before we begin tonight's story, take a quiet moment to settle in and get comfortable. Find a position where your body can fully relax, whether you're lying in bed, resting on a couch, or simply unwinding after a long day. Allow your shoulders to soften. Let your breathing slow down just a little. There is nowhere else you need to be, and nothing else you need to do. Here, on Cozy Sleep Time, we explore calm and gentle topics, stories designed to help the mind slow down and drift peacefully toward rest. Each story moves slowly, gently, allowing your thoughts to wander and your body to relax more and more. Our story tonight is about thunderstorms. As the story unfolds, you can simply listen, or you can allow your mind to drift. There is no need to stay focused. If your thoughts wander, that is perfectly natural. So take one more slow breath, get comfortable, and let the quiet story begin. On a warm summer afternoon, the air feels thick and still. The sun beats down on the earth, heating the ground beneath it. As the ground warms, it radiates heat into the air directly above it, causing that air to become warmer than the surrounding atmosphere. Warm air is lighter than cool air, and so it begins to rise. This rising motion is the very first stirring of what may become a thunderstorm, and it begins with something as simple as a patch of sun-warmed ground, a field of dark soil, or a stretch of asphalt that absorbs the sun's energy more readily than the land around it. The process starts with what meteorologists call an updraft. As warm air rises, it creates a column of upward-moving air that can extend thousands of feet into the sky. This updraft is the engine of the storm, the mechanism that drives everything that follows. The rising air carries with it moisture in the form of water vapor, drawn from the ground, from lakes, from rivers, from the leaves of trees, and the blades of grass. Every surface that holds water contributes a little bit of vapor to the air, and as that air rises, it carries its invisible cargo upward. The amount of moisture in the air is measured by humidity, and on a warm summer day, the humidity can be high enough to provide all the fuel a storm could need. As the air climbs higher, it encounters lower atmospheric pressure. The pressure decreases with altitude, and this decrease allows the rising air to expand. When air expands, it cools. This is a fundamental principle of the atmosphere, known as adiabatic cooling. The cooling causes the water vapor in the air to reach its dew point, the temperature at which the air can no longer hold all of its moisture. When this happens, the water vapor begins to condense into tiny liquid droplets. These droplets are so small that they remain suspended in the air, and by the billions, they form a visible cloud. The process is the same as when your breath fogs on a cold day, only on a scale that stretches across the sky. The cloud that forms at this stage is puffy and white, with a flat base and a rounded top. It is called a cumulus cloud, from the Latin word for heap or pile. On most days, these clouds are harmless. They form in the morning, drift across the sky, and dissipate by evening. But when the atmosphere is sufficiently unstable and the air is moist enough, the updraft that created the cloud does not stop. It continues to feed warm, moist air into the cloud, causing it to grow upward, sometimes at an astonishing rate of several thousand feet per minute. The cloud builds upward because the updraft inside it is stronger than the surrounding air. The air inside the cloud is warmer than the air outside it, so it continues to rise, pushing through the atmosphere like a bubble rising through water. As the rising air punches through layers of the atmosphere, the cloud grows taller and taller. Its top may reach 20,000 feet, then 30,000, then 40,000 feet above the ground. At these altitudes, the temperature is well below freezing, often reaching -50 degrees Fahrenheit or colder. The tiny water droplets in the upper reaches of the cloud begin to freeze, turning into ice crystals. The cloud takes on a new appearance, its top becoming hard and flattened into the shape of an anvil. This is the signature shape of a cumulonimbus cloud, the cloud of a thunderstorm. Inside this towering cloud, powerful forces are at work. The updraft continues to feed the storm, carrying more and more moisture upward at speeds that can exceed 60 miles per hour. The ice crystals in the upper part of the cloud grow larger as they collide with supercooled water droplets, water that remains liquid even below freezing. These collisions cause the ice particles to become electrically charged, a process that will eventually produce lightning. The cloud becomes a churning mass of rising air, falling precipitation, and shifting electrical charges. At any given moment, the cloud contains millions of tons of water in the form of vapor, liquid droplets, and ice crystals. The formation of a thunderstorm depends on three key ingredients. The first is moisture, which provides the fuel for the storm. Without sufficient water vapor in the air, there would be no cloud to speak of, no rain, no lightning. The second ingredient is instability, which means that the air near the ground is significantly warmer than the air above it. The greater the temperature difference, the more vigorously the warm air will rise, and the more powerful the storm can become. The third ingredient is a lifting mechanism, something that forces the warm air to begin its upward journey. This can be a front, where a mass of cool air pushes under warm air and lifts it. It can be a mountain range, which forces air to rise as it flows over the peaks. It can be the sea breeze, where cool air from the ocean pushes inland and lifts the warm air ahead of it. Or it can be something as simple as the sun heating a field of dark soil more than the surrounding forest, creating a localized pocket of warm air that rises on its own. As the updraft continues, it eventually reaches a point where it can no longer support the weight of the precipitation forming within the cloud. The ice crystals and water droplets grow heavy, and they begin to fall. This falling precipitation drags air down with it, creating a downdraft. The downdraft is the counterpart of the updraft, and its arrival marks a turning point in the storm's life. The downdraft spreads out when it reaches the ground, sending cool air rushing outward in all directions. This outflow can be felt as a sudden, cool gust of wind, the first sign that a storm is approaching. The gust front can also lift warm air ahead of it, sometimes triggering the formation of new storms nearby. The entire process, from the gentle rise of warm air to the towering presence of a mature thunderstorm, is a testament to the energy contained within the atmosphere. A single thunderstorm can release as much energy as a nuclear bomb, but it does so gradually over the course of hours in the form of heat, wind, light, and sound. The storm is not a random event, but a natural expression of the atmosphere's attempt to balance itself, to redistribute heat from the surface to the upper levels of the sky. This process of convection is one of the primary ways that the Earth's atmosphere moves heat from the tropics toward the poles, and thunderstorms are a key part of this global system. The formation of a thunderstorm is a cycle of warmth and moisture, of rising and falling, of building and releasing. It begins with the simplest of conditions, a patch of warm ground on a summer day, and builds into one of the most powerful displays that nature has to offer. The same process unfolds countless times across the planet every day, in tropical jungles and desert plains, over mountain ranges and open oceans, a constant, quiet rhythm of the atmosphere that has been playing for as long as the Earth has had an atmosphere to stir. Each storm is a unique expression of this process, shaped by the local conditions of temperature, moisture, and wind. But all of them share the same fundamental origin in the simple act of warm air rising. There is a quiet elegance to how a thunderstorm begins. There is no dramatic starting point, no single moment that marks the beginning. Instead, there is a gradual accumulation of conditions, a slow building of potential, until the atmosphere reaches a tipping point and the air begins to rise. The storm does not start all at once. It starts one warm air parcel at a time, 1 degree of temperature at a time, one invisible wisp of water vapor at a time. By the time the first cumulus cloud appears, the process has been underway for hours, and the storm is already well on its way to becoming what it will be. For those who take the time to understand the formation of thunderstorms, the sky becomes a different place. It is no longer just a backdrop to daily life, but a living system, full of movement and potential. The clouds are not just clouds, but expressions of the atmosphere's inner workings. The warm breeze is not just a breeze, but the first stirring of a process that may, given the right conditions, grow into something far greater. The formation of a thunderstorm is a reminder that the most powerful events often begin in the most humble ways, and that the potential for greatness exists in even the simplest of beginnings. Every thunderstorm follows a pattern, a predictable sequence of development that meteorologists have studied and named. This pattern is called the life cycle of a thunderstorm, and it consists of 3 distinct stages. Each stage has its own character, its own weather, and its own role in the storm's brief existence. Understanding these stages helps to demystify the storm and reveals the orderly process behind what can seem like pure chaos. The storm is not a random event, but a structured process, as predictable in its way as the phases of the moon. The first stage is the cumulus stage. It begins when a pocket of warm air rises from the surface, driven by the heat of the sun or by some other lifting mechanism. As this air rises, it cools and condenses into a cloud. At first, the cloud is small and well-defined, a single cumulus cloud floating in a blue sky. It continues to grow upward as long as the rising air inside it is warmer than the surrounding air. In the cumulus stage, the updraft is the only significant movement within the cloud. There is no rain yet, no thunder or lightning, just the steady, upward flow of air. The cloud is like a balloon being inflated, growing larger and larger as more and more warm air feeds into it. The cloud in the cumulus stage is composed primarily of water droplets. Its edges are sharp and crisp, and it looks much like any other fair-weather cloud, only it is growing. And it keeps growing because the updraft inside it is persistent. The top of the cloud rises higher and higher, pushing into colder regions of the atmosphere. The cloud begins to tower above its neighbors, its top reaching toward the tropopause, the boundary between the lower and middle layers of the atmosphere. The air inside the cloud may be rising at speeds of 30 or 40 miles per hour, carrying enormous amounts of moisture upward. The cloud grows vertically, not horizontally, and it takes on a distinctive cauliflower-like appearance as it builds. The cumulus stage can last anywhere from 10 to 30 minutes. During this time, the cloud is building, accumulating, gathering strength. The water droplets within it are bumping into each other, merging, growing larger. This process is called collision coalescence, and it is how raindrops form. Some of the droplets freeze as they are carried above the freezing level, turning into ice crystals and small hailstones. The cloud is becoming a machine, but it has not yet begun to produce its main output. The rain is still held aloft by the power of the updraft, suspended in the churning air of the growing cloud. The updraft is strong enough to keep even fairly large droplets and ice particles aloft. The transition from the cumulus stage to the mature stage happens when the precipitation in the cloud becomes too heavy for the updraft to support. The rain and hail begin to fall, and as they fall, they drag air with them, creating a downdraft. The arrival of the downdraft marks the beginning of the mature stage. The storm has now become a system of both rising and falling air, a circulation that sustains itself for a time. The coexistence of updraft and downdraft within the same cloud creates a complex interior of competing forces. The mature stage is the most intense part of the storm's life. The updraft and downdraft exist side by side within the same cloud, creating a complex and energetic interior. Rain falls from the base of the cloud, sometimes in torrents. Lightning flickers within and between the clouds, and thunder rolls across the sky. Hail may fall if the updraft is strong enough to keep ice particles aloft long enough for them to grow to significant size. The top of the cloud has spread out into the familiar anvil shape, flattened by the winds at high altitude. The anvil can extend for many miles downwind of the storm, a broad, flat cap that marks the top of the storm cloud. At the surface, the mature stage brings the full force of the storm. Heavy rain, strong winds, and frequent lightning are all typical. The downdraft reaches the ground and spreads out, creating a gust front that can be felt as a sudden drop in temperature and a sharp increase in wind speed. This cool outflow can kick up dust and debris, and it often signals to anyone outdoors that the storm has arrived in full force. The temperature can drop by 10 or 15 degrees in a matter of minutes as the cold outflow arrives. The gust front can also lift warm air ahead of it, sometimes triggering new storms nearby. The mature stage can last from 20 to 60 minutes, depending on the strength of the storm and the conditions in the surrounding atmosphere. During this time, the storm is at its most dangerous. It can produce damaging winds, large hail, flash flooding, and tornadoes. The lightning is frequent and intense, and the rain can be so heavy that visibility drops to near zero. The rain rates can exceed several inches per hour, overwhelming drainage systems and causing rapid flooding. This is the storm at its peak, the culmination of all the energy that has been building since the first warm air began to rise. Eventually, the downdraft begins to dominate the storm. The updraft that fed the storm is gradually cut off by the spreading outflow of cool air at the surface. When the updraft is no longer able to sustain itself, the storm enters its third and final stage, the dissipating stage. In this stage, the downdraft has taken over the entire cloud. The rain becomes lighter and more widespread, changing from a heavy downpour to a steady, gentle shower. The lightning becomes less frequent, and the thunder fades to distant rumbles. The storm is running out of energy, like a fire that has consumed all of its fuel. The cloud itself begins to break apart. Without the updraft to supply moisture, the cloud can no longer maintain its structure. The sharp, crisp edges of the cumulus stage and the towering presence of the mature stage give way to a ragged, diffuse appearance. The anvil top may remain for a while, a lingering reminder of the storm that was. The cloud begins to evaporate, its edges fraying and its base rising. The rain that continues to fall is the last of the moisture that had been stored in the cloud. But eventually, even the anvil dissolves and the sky clears. The dissipating stage can last for an hour or more. During this time, the storm is releasing its last energy. The rain that falls is what remains of the moisture that was not converted into runoff or evaporation. The downdraft weakens as the temperature difference between the storm and its surroundings decreases. The storm is no longer generating new energy. it is simply winding down, like a clock running out of power. Eventually, the cloud disappears entirely, and the sky returns to the state it was in before the storm began, often clearer and cooler than before. The entire life cycle of a typical thunderstorm, from the first cumulus cloud to the final dissipation, lasts about an hour or two. In that time, the storm has moved across the landscape, sometimes traveling many miles, and has released the energy that was stored in the warm, moist air near the surface. The storm is a transient thing, here for a brief time and then gone. But in its passing, it has changed the atmosphere around it, cooling the air, redistributing moisture, and leaving behind the fresh, clean smell that follows a good rain. The storm has done its work, and the atmosphere is the better for it. This cycle repeats itself countless times, every day, in every part of the world where the conditions are right. Each storm is unique in its details, in its strength, in its duration, and in its path. But each one follows the same three stages, the same pattern of building, peaking, and fading. It is a rhythm as old as the atmosphere itself, and it continues, season after season, year after year, without pause. The life cycle of a thunderstorm is one of the fundamental patterns of weather, a cycle that has been repeating for billions of years and will continue for billions more. There is a certain comfort in knowing that a thunderstorm follows a predictable pattern. The storm is not chaotic, even when it appears to be. It is following a script that has been written by the laws of physics, a script that meteorologists have learned to read. The cumulus stage tells us that the storm is building. The mature stage tells us that the storm is at its peak. The dissipating stage tells us that the storm is winding down. Knowing these stages allows us to watch a storm with understanding, to appreciate where it is in its life cycle, and to know what to expect next. The storm becomes not a frightening unknown, but a familiar process, one that we can watch with calm and interest. The three stages of a thunderstorm also reflect a broader truth about the natural world. Everything that rises must eventually fall. Everything that builds must eventually decay. The storm follows the same path that all things follow, from beginning to middle to end. And just as the dissipating stage makes way for clear skies, the endings in our own lives make way for new beginnings. The storm teaches us that endings are not failures but completions, natural parts of a cycle that will begin again somewhere else, with a new pocket of warm air rising on a new summer afternoon. Among all the phenomena associated with thunderstorms, lightning and thunder are the most striking. They are the visible and audible signatures of the storm, the elements that capture our attention and remind us of the power contained within the atmosphere. The science of lightning and thunder is a story of electrical charge, of extreme temperatures, and of sound traveling through the air. It is a story that has fascinated scientists for centuries and that continues to reveal new mysteries. Inside a thunderstorm cloud, the churning motion of the updrafts and downdrafts causes collisions between different types of particles. Small ice crystals, called graupel or soft hail, are tossed about within the cloud. As they collide with larger ice particles and with supercooled water droplets, electrons are transferred from one particle to another. The lighter ice crystals tend to lose electrons and become positively charged, while the heavier graupel particles gain electrons and become negatively charged. This process is called the non-inductive charging mechanism, and it is the primary way that thunderstorms become electrified. The updrafts carry the lighter, positively charged particles to the upper part of the cloud, while the heavier, negatively charged particles settle in the middle and lower parts of the cloud. This separation of charge creates an enormous electrical field within the cloud. The top of the cloud becomes positively charged, and the middle and bottom become negatively charged. Meanwhile, the negative charge at the bottom of the cloud repels electrons on the ground below, inducing a positive charge on the surface. The ground beneath the storm becomes positively charged, and the storm cloud becomes a giant capacitor, storing electrical energy. The electrical field within the storm can reach hundreds of thousands of volts per meter, enough to break down the insulating properties of air. When the electrical field becomes strong enough, it overcomes the insulating properties of the air. The air, which is normally a good insulator, breaks down under the stress of the electrical field, and a path of ionized air forms. This path is called a stepped leader, and it moves downward from the cloud in a series of rapid steps, each step advancing the leader closer to the ground. The stepped leader is invisible to the naked eye, but it is the first stage of what will become a visible lightning bolt. The leader advances in steps of about 150 feet at a time, pausing briefly between each step as it probes the air for the path of least resistance. As the step leader approaches the ground, it draws upward from the ground a connecting discharge, a streamer of positive charge that rises to meet it. When the two paths connect, a complete circuit is formed, and a massive electrical current flows along the ionized channel. This return stroke is what we see as the brilliant flash of lightning. The return stroke travels upward at a speed of up to 100 million feet per second, and it heats the air around it to a temperature of approximately 50,000 degrees Fahrenheit. That is 5 times hotter than the surface of the sun. In that instant, the air along the lightning channel becomes a plasma, a fourth state of matter in which electrons have been stripped from their atoms. The extreme heating of the air causes it to expand explosively. The air along the lightning channel is heated so rapidly that it cannot move out of the way fast enough. Instead, it pushes outward in a shock wave, a wall of compressed air that travels faster than the speed of sound. Within a few feet of the lightning channel, this shock wave is incredibly intense, with a pressure thousands of times greater than normal atmospheric pressure. As it travels outward, it slows down and becomes an ordinary sound wave, and it is this sound wave that we hear as thunder. Thunder is the sound of air expanding violently after being superheated by lightning. The characteristic rumble of thunder comes from the fact that the lightning channel is not a straight line, but a twisted, branching path. Different parts of the channel are at different distances from the observer, so the sound arrives at different times. The sound from the nearest part of the channel arrives first, followed by the sound from more distant parts. The result is the long, rolling rumble that we associate with thunder. The sound waves also reflect off the ground and off clouds, creating echoes that add to the complexity of the sound. The distance to a lightning strike can be estimated by counting the seconds between the flash and the thunder. Sound travels at approximately 1,100 feet per second, or about 1 mile every 5 seconds. By counting the seconds between the flash and the thunder and dividing by 5, you can estimate the distance in miles. A 5-second gap means the lightning struck about 1 mile away. A 10-second gap means 2 miles. This simple technique is one of the oldest tools of thunderstorm observation and a useful way to track the approach or departure of a storm. There are different types of lightning. Cloud-to-ground lightning is the type that most people think of when they imagine lightning. It strikes downward from the cloud to the ground, and it is the most dangerous type, responsible for most lightning injuries and deaths. Intracloud lightning occurs within a single cloud between areas of opposite charge. It is the most common type of lightning, accounting for the majority of flashes that we see flickering inside storm clouds. Cloud-to-cloud lightning travels between different clouds, and cloud-to-air lightning strikes from a cloud into the clear air beyond it. Each type plays a role in the electrical activity of the storm. Some lightning does not reach the ground. A bolt from the blue is a type of cloud-to-ground lightning that originates in a distant storm and travels through clear air before striking the ground far from the storm itself. These bolts can be particularly dangerous because they can strike without warning, under a clear sky, up to 10 miles or more from the parent storm. There is also heat lightning, which is simply lightning from a distant storm that is too far away for the thunder to be heard. It is called heat lightning because it often occurs on hot summer nights when storms are active far over the horizon, and all that reaches the observer is the silent flickering of light. The study of lightning is an ongoing field of research. Scientists use a variety of tools to study lightning, including high-speed cameras that capture the progression of the stepped leader, radio receivers that detect the electromagnetic pulses of lightning, and satellite-based sensors that map global lightning activity. They have learned that a single lightning flash can contain multiple return strokes, all following the same ionized channel, creating a flickering effect that our eyes perceive as a single flash. They have also learned that lightning can trigger other lightning, as the electrical field of one discharge influences the field around it, creating a cascade of strikes. For all its power, lightning is a fleeting thing. Each flash lasts only a fraction of a second, yet in that instant, it releases a tremendous amount of energy. The energy in a single lightning bolt could power a home for several days if it could be captured and stored. But lightning is not easily controlled. It is a wild and unpredictable force, following paths determined by the subtle variations in the electrical field and the conductivity of the air. Lightning is also essential to life on Earth, as it fixes nitrogen in the atmosphere, converting it into a form that plants can use. Each lightning bolt creates nitrogen oxides that are washed to the ground by rain, providing natural fertilizer. The relationship between lightning and thunder is one of cause and effect, of light and sound. The flash comes first, traveling at the speed of light, reaching our eyes in an instant. The thunder follows, traveling at the speed of sound, arriving a few seconds later for every mile between us and the strike. This delay between the flash and the thunder is a daily reminder of the difference between the speed of light and the speed of sound, a subtle lesson in physics delivered by every passing storm. The light and the sound are two expressions of the same event, two ways of experiencing the same powerful discharge of energy. Lightning and thunder are not just scientific phenomena, they are also deeply human experiences. The flash of lightning has inspired artists and writers for centuries. The crack of thunder has been the voice of gods in countless mythologies. Even with our modern understanding of the science behind them, lightning and thunder retain their power to move us. They remind us that the world is full of forces greater than ourselves, that the atmosphere above us is alive with energy, and that there is still wonder to be found in looking up at the sky. There is also a practical beauty to the relationship between lightning and thunder. The simple act of counting the seconds between the flash and the sound gives us a way to measure the storm, to track its approach and its departure. It turns the storm into something we can interact with, something we can read and understand. The count becomes a ritual, a way of connecting with the storm. 1 1000, 2 1000, 3 1000. The storm is 3 miles away. 4 1000, 5 1000. The storm is getting closer. The count continues, and with each second, our understanding of the storm deepens. Not all thunderstorms are the same. While they all share the basic ingredients of moisture, instability, and a lifting mechanism, they can take different forms depending on the conditions in the atmosphere. Meteorologists classify thunderstorms into several types, ranging from the simplest and most brief to the most complex and long-lived. Each type has its own structure, its own behavior, and its own potential for severe weather. Understanding these types helps forecasters predict what a storm will do and how dangerous it might become. The simplest type is the single-cell thunderstorm. Also called a pulse storm, this is the classic thunderstorm that forms on a summer afternoon and runs through its life cycle in about an hour. It consists of a single updraft and a single downdraft, and it follows the three-stage process of cumulus, mature, and dissipating. Single-cell storms are usually not severe, though they can produce brief periods of heavy rain, occasional lightning, and sometimes small hail. They are the most common type of thunderstorm, and they are the ones that most people experience on a regular basis. They are the storms that pop up on a hot afternoon and are gone by dinner time. A single-cell storm forms when a local pocket of warm air rises and creates a cumulus cloud. The storm develops, produces rain and lightning for a short time, and then dissipates as the downdraft cuts off the updraft. The entire process takes place in one location, with the storm moving only as the wind aloft carries it. These storms are relatively weak because they do not have a mechanism to sustain themselves beyond their natural life cycle. They rely entirely on the initial supply of warm, moist air, and once that supply is exhausted, the storm ends. They are the simplest expression of the thunderstorm process. The second type is the multi-cell thunderstorm. A multi-cell storm is a cluster of individual thunderstorm cells at different stages of development. As one cell matures and begins to dissipate, its outflow triggers the formation of a new cell adjacent to it. This process can continue for hours, with new cells forming on the flank of the old ones, creating a chain of storms that moves across the landscape. Multi-cell storms are more organized and longer-lived than single-cell storms, and they can produce severe weather, including damaging winds, large hail, and heavy rain. A multi-cell storm can last for many hours and travel hundreds of miles. The key to the multi-cell storm is the gust front. When the downdraft of a mature cell reaches the ground, it spreads out in all directions. The leading edge of this cool air acts as a miniature cold front, lifting the warm, moist air ahead of it. If the conditions are right, this lifted air can form a new thunderstorm cell. The new cell then matures, produces its own downdraft, and triggers another cell. The result is a family of storms, each one living out its life cycle in sequence, like a line of candles being lit one after another. The entire complex moves together, with new cells forming on one side and old cells dissipating on the other. Multi-cell storms can produce a variety of severe weather. They are capable of producing hail of significant size, winds that can damage structures, and heavy rain that can cause flash flooding. They can also produce tornadoes, though the tornadoes associated with multi-cell storms are usually weak and short-lived. The line of storms that forms along a gust front is called a squall line, and it can stretch for hundreds of miles, producing severe weather across a wide area. Squall lines are common in the spring and summer in many parts of the world. The third and most powerful type is the supercell thunderstorm. A supercell is a thunderstorm that contains a deep, rotating updraft called a mesocyclone. This rotation is what sets the supercell apart from other types of thunderstorms. The updraft in a supercell rotates because of wind shear, a change in wind speed or direction with height. When the wind at the surface is from the south and the wind at higher altitudes is from the west, the updraft can begin to spin. This spinning updraft gives the supercell its characteristic structure and its tremendous longevity. Supercells are the least common type of thunderstorm, but they are the most dangerous. They can persist for many hours, traveling hundreds of miles, and they are capable of producing all forms of severe weather. Large hail, damaging winds, and torrential rain are all common in supercells, but the most notable product of a supercell is the tornado. Most significant tornadoes are produced by supercells, and the largest and most violent tornadoes almost always come from supercells. A supercell can produce a tornado that stays on the ground for an hour or more, carving a path of destruction across many miles. The structure of a supercell is distinctive. On radar, it appears as a hook echo, a shape that looks like a hook attached to the main body of the storm. This hook is produced by the rotating updraft, which wraps precipitation around it. In person, a supercell can be a terrifying and beautiful sight. The base of the cloud is often dark and low, and the rotating wall cloud from which tornadoes form may be visible beneath it. The rain and hail fall to the north or northwest of the updraft, leaving the area around the mesocyclone relatively clear. This clear area, called the vault or the bounded weak echo region on radar, is where the strongest updraft is located. There is also a type of thunderstorm that forms in environments with very low wind shear. These are sometimes called air mass thunderstorms, and they are essentially single-cell storms that form within a uniform air mass. They are typically weak and short-lived, and they often form in the afternoon and dissipate by evening. They are the most common type of thunderstorm in tropical regions, where the atmosphere is often unstable but wind shear is low. These storms are the ones that produce the daily afternoon rain in many tropical locations. Another classification of thunderstorms is based on the organization of the storm system. A mesoscale convective system, or MCS, is a large complex of thunderstorms that persists for many hours and covers a large area. MCSs are common in the central United States during the spring and summer, and they can produce widespread heavy rain, strong winds, and frequent lightning. An MCS can be composed of many individual thunderstorm cells, organized into a cohesive system that moves across the landscape. Some MCSs are so large that they can be seen from space, covering areas the size of entire states. Each type of thunderstorm represents a different balance of the forces that drive storm formation. Single-cell storms are the simplest expression of those forces. Multi-cell storms show how storms can organize and sustain themselves through their own outflow. Supercells represent the most organized and powerful form of thunderstorm, a storm that can persist for hours and produce some of the most extreme weather on Earth. And mesoscale convective systems show how storms can organize on the largest scales, affecting weather across entire states or regions. The study of thunderstorm types is not just an academic exercise. It has practical applications in weather forecasting and severe weather warnings. By identifying the type of thunderstorm that is forming, forecasters can predict what kind of weather it is likely to produce and issue appropriate warnings. A supercell requires a tornado warning and immediate action. A multi-cell storm may require a severe thunderstorm warning. A single-cell storm may require nothing more than an advisory. Understanding the different types of thunderstorms helps us to be prepared and to stay safe, and it deepens our appreciation for the variety and complexity of the storms that share our sky. Each type of thunderstorm is a different expression of the same basic process, a different response to the conditions that the atmosphere provides. The single-cell storm is the default, the baseline thunderstorm that forms when the conditions are adequate but not exceptional. The multi-cell storm is the cooperative storm, a system that works together to sustain itself beyond the life of any single cell. The supercell is the exceptional storm, the one that forms when the conditions are just right and the atmosphere provides the organization and energy for something truly powerful. The variety of thunderstorm types is a reminder that nature does not repeat itself exactly. Every storm is different, shaped by the unique combination of conditions at the time and place of its formation. No two thunderstorms are identical, just as no two snowflakes are identical. This variety is part of what makes thunderstorms so fascinating to study. There is always something new to learn, always a new variation to observe. The storms that share our sky are as diverse as the landscapes they form over, and they deserve our attention and our respect. Thunderstorms are powerful natural events, and they deserve our respect. While they are fascinating to watch and study, they also pose real dangers. Knowing how to stay safe during a thunderstorm is an essential part of living with these storms. The principles of thunderstorm safety are simple and easy to remember, and they can make the difference between a close call and a tragedy. Safety during a thunderstorm is largely a matter of being prepared and making sensible decisions. The most immediate danger during a thunderstorm is lightning. Lightning strikes the earth approximately 100 times every second, and while the odds of being struck in any given year are low, the consequences can be severe. Lightning can cause cardiac arrest, neurological damage, burns, and death. The first rule of thunderstorm safety is to seek shelter indoors when thunder is heard. If you can hear thunder, you are within striking distance of lightning. The safe place is a substantial building with 4 walls and a roof, or a metal-topped vehicle with the windows closed. Open structures like picnic shelters, bus stops, and sheds do not provide adequate protection. Once inside, there are still precautions to take. Lightning can travel through plumbing and electrical systems. During a thunderstorm, it is best to avoid running water, including showers, baths, and dishwashing. The electrical wiring in a building can also conduct lightning, so it is wise to avoid using corded electronics and appliances. Cordless phones, cell phones, and other battery-powered devices are safe to use because they do not provide a direct path to the outside. Unplugging sensitive electronics before the storm arrives can prevent damage from power surges. It is also advisable to stay away from concrete floors and walls, as they may contain metal reinforcing bars that can conduct electricity. The safest place in a building during a thunderstorm is an interior room away from windows. While modern buildings are designed to withstand lightning strikes, windows can break from the shock wave of nearby lightning or from flying debris during strong winds. Staying away from windows also reduces the risk of injury from broken glass. Basements and interior hallways are good choices. If you are in a high-rise building, stay on the lower floors if possible. The higher floors are more exposed to lightning strikes and to the effects of strong winds. If you are caught outside during a thunderstorm and cannot reach a safe building or vehicle, there are steps to take that can reduce your risk. The key is to avoid being the tallest object in the area and to avoid conductive paths that lightning might follow. Stay away from open fields, hilltops, and elevated areas. Avoid isolated trees, which are frequent lightning targets. Stay away from bodies of water, which conduct electricity. If you are in a forest, seek shelter under a low clump of small trees, rather than under a single tall tree. If you are in an open area, crouch down with your feet together and your head low, minimizing your contact with the ground. Do not lie flat on the ground, as this increases the area of your body that could be contacted by a ground current. Contrary to popular belief, lightning can strike the same place twice, and it often does. Tall structures like skyscrapers and radio towers are struck repeatedly. The Empire State Building is struck about 25 times per year. So the idea that a location is safe because it has already been struck is a dangerous misconception. Lightning is not selective in that way. It follows the path of least resistance. And if a location offers a good path to ground, it will be struck again and again. The lightning rod was invented precisely because certain places need to be struck regularly, and it is better to control where the strike goes. The second major danger of thunderstorms is flooding. Heavy rain from a thunderstorm can cause flash flooding, which is the leading cause of thunderstorm-related deaths in many parts of the world. Flash flooding occurs when the rain falls faster than the ground can absorb it, causing water to rise rapidly. It can happen in urban areas where pavement prevents absorption, in low-lying areas where water collects, and in narrow canyons and arroyos where water funnels through confined spaces. Flash flooding can occur within minutes of heavy rain, giving very little warning. The most important rule for flash flood safety is never to drive through standing water. It takes only a small amount of moving water to sweep a vehicle off the road. 6 inches of water can cause a car to lose control, and 12 inches can sweep a car away. If you encounter a road covered with water, turn around and find another route. Do not attempt to walk through moving water either. Just 6 inches of fast-moving water can knock a person off their feet. Many flood deaths occur when people underestimate the power of moving water. The third danger is damaging wind. Thunderstorms can produce straight-line winds in excess of 100 miles per hour, winds that can knock down trees, power lines, and structures. During a severe thunderstorm warning, stay away from windows and move to an interior room on the lowest floor of the building. If you are in a mobile home, seek shelter elsewhere. Mobile homes offer little protection from high winds and are particularly vulnerable to being overturned. Even anchored mobile homes can be damaged by severe thunderstorm winds. Large hail is another hazard. Hail can range in size from small pebbles to grapefruits, and it falls at high speed. Large hail can cause serious injury and significant property damage. During a hailstorm, stay indoors and away from windows. If you are driving, pull over to a safe location and stay inside the vehicle, covering your head and eyes. Hail can shatter windshields, so do not try to outrun a hailstorm in a car. If you can, find a covered parking area or a building to wait out the hail. If you are in a vehicle during a severe thunderstorm, it is generally safest to stay inside the vehicle with the windows closed. Vehicles provide good protection from lightning because the metal frame conducts the electrical current around the occupants and into the ground. However, vehicles offer less protection from high winds and flooding. If the storm includes a tornado warning, seek shelter in a sturdy building. A vehicle is not safe in a tornado. If you are in a vehicle and cannot reach a building during a tornado warning, the safest option is to get out and lie flat in a low area, such as a ditch. There is a simple phrase that captures the essence of thunderstorm safety. When thunder roars, go indoors. This phrase is easy to remember and easy to follow. It means that as soon as you hear thunder, it is time to move to a safe location. Do not wait for the rain to start. Do not wait to see if the storm will pass. The moment you hear thunder, you are at risk. Go indoors and stay there until 30 minutes after the last clap of thunder. This is called the 30-minute rule, and it ensures that the storm has moved far enough away that the lightning risk has decreased to a safe level. Thunderstorm safety is about being prepared and making good decisions. Check the weather forecast before heading outdoors. Have a plan for where you will go if a storm develops. Keep an eye on the sky and be aware of changing conditions. Storms can develop quickly, sometimes in as little as 30 minutes. By staying informed and knowing what to do, you can enjoy the beauty of thunderstorms while staying safe from their dangers. The goal of thunderstorm safety is not to fear the storm, but to respect it, to understand its dangers, and to know how to respond so that you can weather any storm with confidence. Safety during a thunderstorm is not complicated, but it does require awareness. The key is to pay attention to the weather and to have a plan. Know where you will go when thunder roars. Have a safe place identified, whether at home, at work, or while traveling. Share this knowledge with your family and friends so that everyone knows what to do. A few minutes of preparation can make all the difference when a storm arrives. It is also worth remembering that thunderstorms are not something to be feared. They are a natural part of the weather, as normal as sunshine or snowfall. With proper precautions, they can be enjoyed from a place of safety. The goal is not to avoid thunderstorms, but to coexist with them, to appreciate their beauty while respecting their power. By understanding the dangers and knowing how to respond, we can transform the thunderstorm from a source of anxiety into a source of wonder. The storm becomes not something to fear, but something to observe, to learn from, and to appreciate, all from the safety of a well-chosen shelter. There is a particular quality to the sound of a thunderstorm that has captivated people for as long as there have been people to listen. It is a sound composed of many layers, each with its own character and rhythm. The sound of a thunderstorm is not a single note, but a symphony, and like all symphonies, it has its quiet passages and its crescendos, its gentle moments and its powerful ones. To listen to a thunderstorm is to hear the atmosphere at work, and it is an experience that engages the ear as fully as the eye. The first sound of an approaching storm is often the wind. Before the rain begins and before the thunder is heard, the wind picks up, rustling through the leaves of trees and carrying with it the smell of damp earth and rain. The wind has a sound of its own, a low, steady rush that builds as the storm draws nearer. It is the sound of air in motion, of the atmosphere adjusting itself, and it is the first sign that something is about to change. The wind can be gentle at first, a soft breeze that barely stirs the grass, but it grows steadily as the storm approaches, becoming a persistent presence. Then comes the rain. At first, it is just a few scattered drops, each one making a distinct sound as it lands on a leaf, a rooftop, or the ground. The sound of these first drops is sharp and individual, each one separate from the next. They land with a soft tap, a gentle announcement of what is to come. But as the rain intensifies, the individual drops merge into a continuous sound, a steady hiss that fills the air. The sound of rain varies depending on what it falls upon. On a metal roof, it is a loud, rhythmic drumming that can be heard throughout the house. On a leafy tree, it is a soft patter. On the ground, it is a gentle hiss. On a window, it is a series of taps and streams. The sound of rain is one of the most soothing sounds in nature. It is a white noise that masks other sounds and creates a sense of enclosure and safety. The steady rhythm of rain has a calming effect on the human mind, slowing our thoughts and relaxing our bodies. It is a sound that tells us that we are sheltered, that the storm is outside and we are inside, that we are safe. This is perhaps why the sound of rain on a roof is so universally beloved. It creates a cocoon of sound that separates the inside from the outside, a sonic blanket that wraps around us. As the storm intensifies, the thunder begins. Thunder is not a simple sound. It is a complex sequence of sounds that begins with a sharp crack or a low rumble and builds into a prolonged roar. The character of thunder depends on the distance and orientation of the lightning channel. Close lightning produces a sharp, explosive crack, a sound that can be startling in its suddenness. This crack is the sound of the air being violently displaced by the extreme heat of the lightning channel. It is followed by a rapid series of pops and rattles as the sound travels along the branches of the lightning channel. Distant thunder has a different quality. It is a low, rolling rumble that seems to come from all directions at once. This rumble is the sound of the thunder having traveled for miles, its high frequencies absorbed by the air and only the low frequencies remaining. The rumble can last for many seconds, fading slowly in and out as the sound waves from different parts of the lightning channel arrive at different times. The rolling quality of distant thunder is what gives it its name, as it seems to roll across the sky like a great stone tumbling down a hill. The low frequency of distant thunder can also be felt as a vibration in the chest, a physical sensation that accompanies the sound. The interplay between rain and thunder creates the characteristic soundscape of a thunderstorm. During the peak of the storm, the rain is at its heaviest and the thunder is at its loudest and most frequent. The rain provides a continuous background of sound, a steady rhythm that underlies everything else. The thunder punctuates this background with sudden, dramatic moments, each one a burst of sound that rises above the rain and then fades away. The combination is dynamic and ever-changing, never quite the same from one moment to the next. The sound of a thunderstorm is different every time, shaped by the unique character of each individual storm. The wind adds another layer to the sound. During the peak of the storm, the wind can be strong enough to create its own sounds, a howling or whistling as it passes around buildings and through trees. The wind adds a sense of motion and energy to the soundscape, a reminder that the storm is a living thing, moving and changing. The sound of wind and rain and thunder together creates a powerful sensory experience, one that engages not just our ears, but our whole sense of being in the world. The wind can also create sounds that are unique to the built environment, whistling through window frames or rattling loose shingles. In the aftermath of the storm, the sounds change again. The rain becomes lighter, a gentle shower rather than a downpour. The thunder becomes more distant, its rumbles softer and less frequent. The wind dies down to a breeze, and gradually, the storm sounds give way to the sounds that follow. The dripping of water from leaves and eaves creates a gentle percussion, a slow rhythm that marks the passing of the storm. The occasional rumble from a distant lightning strike reminds us that the storm has not entirely left us. And then eventually, the sounds of the world returning to normal begin to emerge. The birds singing, the insects buzzing, the sounds of everyday life resuming. Each sound is a step away from the intensity of the storm and back toward the ordinary. The sound of a thunderstorm has been recorded and listened to by people all over the world. Sound recordings of thunderstorms are used for relaxation, for meditation, for sleep. There is something about the sound of a storm that speaks to a deep part of us, that connects us to the natural world and to a sense of peace. Perhaps it is the knowledge that the storm is both powerful and temporary, that it will pass, that the sun will come out again. Perhaps it is simply the beauty of the sound itself, the complexity and richness of a natural symphony that has been playing for billions of years. To listen to a thunderstorm is to be in the presence of something ancient and powerful. It is to hear the sound of the atmosphere doing its work, redistributing heat and moisture, balancing the energy of the planet. The sound of thunder and rain is the sound of the earth breathing, of the great cycles of weather that sustain life, and it is a sound that, for all its power, can bring a deep and lasting calm to those who hear it. The sound of the storm is one of nature's greatest gifts, a symphony that plays for free, as often as the weather chooses to perform. The sound of a thunderstorm is a reminder that the world is full of music if we only take the time to listen. The rain has its rhythm, the thunder its dynamics, the wind its melody. Together, they create a composition that no human composer could replicate, a piece that is different every time it is played. The storm is a living orchestra, and we are its audience, invited to listen whenever the weather chooses to perform. For those who find peace in the sound of a thunderstorm, the experience is deeply personal. The sound becomes a backdrop for thought, a companion in solitude, a lullaby for sleep. It is a sound that connects us to the earth and to the sky, to the ancient rhythms of the planet. In listening to the storm, we are participating in something that humans have experienced for tens of thousands of years, a shared sonic experience that links us to our ancestors and to all the generations that will come after us. The sound of thunder and rain is one of the oldest sounds on Earth, and it continues to speak to us today with the same power it has always had. The sound of a thunderstorm also has a way of bringing people together. In many cultures, the first clap of thunder is a signal to gather, to check on loved ones, to share the experience of the storm. The sound of the storm becomes a shared reference point, a common experience that everyone in a community can relate to. The storm is a reminder that we are all in the same weather, all under the same sky, all subject to the same forces. The sound of the storm is the sound of our shared vulnerability and our shared resilience. Thunderstorms occur on every continent except Antarctica, and they occur over the oceans as well. They are a global phenomenon, a fundamental part of the Earth's weather system, but the frequency and character of thunderstorms vary greatly from one part of the world to another, shaped by geography, climate, and the patterns of the atmosphere. Some places experience thunderstorms almost every day, while others go years between storms. This variation tells us a great deal about how the atmosphere works and about the conditions that favor storm formation. The most thunderstorm-prone place on Earth is a region of the Democratic Republic of the Congo in Central Africa. The village of Kifuka receives an average of 158 thunderstorm days per year. This means that on nearly half the days of the year, the people of Kifuka can expect to hear thunder. The reason for this extraordinary frequency is the combination of intense tropical heat and abundant moisture. The warm, humid air of the Congo Basin rises readily, forming thunderstorms that are among the most frequent on Earth. The region's location near the equator ensures year-round warmth, and the dense tropical forests provide a steady source of moisture. Other parts of the world also have high thunderstorm frequencies. The Lake Victoria region of East Africa experiences frequent thunderstorms, as does the island of Java in Indonesia. In South America, the region around the Amazon basin and the foothills of the Andes produces some of the most intense thunderstorms on the planet. These tropical regions have the ideal conditions for thunderstorm formation: heat, moisture, and atmospheric instability. The thunderstorms in these regions are often part of the daily weather pattern, occurring with such regularity that people plan their days around them. The United States has some of the most severe thunderstorms in the world, particularly in a region known as Tornado Alley. This region, which includes parts of Texas, Oklahoma, Kansas, Nebraska, and the Dakotas, has a unique combination of geographical features that makes it a thunderstorm hotspot. Warm, moist air from the Gulf of Mexico flows northward and meets dry, cool air from the Rocky Mountains and cold air from Canada. The collision of these different air masses creates the perfect conditions for severe thunderstorms, including supercells and tornadoes. The spring and early summer months are the most active time, when the temperature contrasts between the air masses are at their greatest. Central Florida also has a very high frequency of thunderstorms. The Florida Peninsula is surrounded by warm water on 3 sides, providing a constant supply of moisture. The sea breeze from the Atlantic Ocean and the Gulf of Mexico converge over the center of the state, forcing air upward and triggering thunderstorms almost daily during the summer months. The city of Tampa is often called the lightning capital of the United States, and the area around it sees more lightning strikes per square mile than almost any other place in the country. On a typical summer afternoon in Florida, storms can be seen developing in multiple locations at once. The Indian subcontinent experiences some of the most dramatic thunderstorms in the world during the pre-monsoon season. Before the rains of the monsoon arrive, the heat builds to an intense degree. The hot, dry air of the interior meets the moist air from the surrounding seas, creating violent thunderstorms that can produce extreme winds, hail, and lightning. These storms are called nor'westers in Bangladesh and parts of eastern India, and they are responsible for significant damage each year. The storms are particularly common in the spring, when the temperature contrast between the land and the sea is at its maximum. In Europe, thunderstorms are less frequent than in the tropics or the United States, but they still occur regularly. The Mediterranean region experiences thunderstorms, particularly in the autumn when the sea is still warm and the air above it begins to cool. Central and Northern Europe see thunderstorms during the summer months, often associated with cold fronts moving in from the Atlantic. The frequency is lower than in more tropical regions, but European storms can still be severe. The Alps and other mountain ranges can trigger localized thunderstorms as air is forced upward over the peaks. Australia experiences thunderstorms across much of the continent. The northern parts of Australia, in the tropics, have frequent thunderstorms during the summer monsoon season. The southeastern part of the country, including the Sydney region, experiences thunderstorms in the spring and summer, often associated with the passage of cold fronts. The interior of Australia, which is dry most of the year, can experience thunderstorms when moisture from the north penetrates into the arid regions. These storms can be particularly dramatic as the dry air produces intense downdrafts and dust storms. The oceans also have thunderstorms. In fact, there are more thunderstorms over the oceans than over land, but most of these oceanic storms go unseen by humans. They form over the warm waters of the tropics, where the sea surface temperature is above 80 degrees Fahrenheit. These storms can be intense, but they are rarely observed except by satellites and by the occasional ship that passes through them. The Intertropical Convergence Zone, a belt of low pressure that circles the Earth near the equator, is a region of near-constant thunderstorm activity. This band of storms stretches around the globe, a permanent feature of the planet's weather. The frequency of thunderstorms varies with the seasons. In most parts of the world, thunderstorms are most common in the spring and summer, when the surface is warmest and the air is most unstable. In the tropics, the thunderstorm season is often tied to the rainy season, when the most moisture is available. In the middle latitudes, thunderstorms are rare in the winter, when the air is too cold and dry to support them. There are exceptions, though. In some coastal regions, thunderstorms can occur in the winter when cold air moves over warm water, creating instability. These winter storms can be especially dangerous because people are less prepared for them. Mountain ranges influence thunderstorm patterns. The Rocky Mountains in North America, the Andes in South America, and the Himalayas in Asia all affect the flow of air and the formation of storms. As air is forced to rise over mountain ranges, it cools and condenses, often triggering thunderstorms. The leeward sides of mountains, where the air descends and warms, tend to be drier and have fewer storms. This is why the eastern slopes of the Rockies see more storms than the western slopes in some regions. Mountains can also create their own local wind patterns that trigger storms on a daily basis. Climate change is expected to affect thunderstorm patterns around the world. As the planet warms, the atmosphere can hold more moisture, which provides more fuel for thunderstorms. Some studies suggest that thunderstorms will become more intense in the future, even if they do not become more frequent. The regions that are already prone to severe thunderstorms may see even more extreme storms in the coming decades. Understanding these changes is an active area of research for climate scientists, and it has important implications for how we prepare for and respond to severe weather. The global distribution of thunderstorms is a map of heat and moisture, of colliding air masses and rising air. It is a map of the Earth's weather system in motion. From the humid jungles of the Congo to the plains of Kansas, from the islands of Indonesia to the mountains of Argentina, thunderstorms are a constant presence, a reminder that the atmosphere is always working, always moving, always seeking balance. Every day, somewhere on Earth, a thunderstorm is forming, maturing, and dissipating, part of a cycle that has been repeating for as long as the Earth has had an atmosphere. The storms of the world connect us all under one sky. Thunderstorms are one of the most democratic phenomena in nature. They occur in rich countries and poor countries, in cities and in wilderness, over land and over sea. They do not respect borders or boundaries. A thunderstorm that forms over the plains of Africa is governed by the same physics as a thunderstorm that forms over the plains of Kansas. The same processes of warm air rising, of moisture condensing, of charge separating are at work everywhere. In this sense, thunderstorms are a universal language, a common experience that unites people across cultures and continents. The global distribution of thunderstorms also reminds us of the interconnectedness of the Earth's weather systems. A thunderstorm in one part of the world can affect weather thousands of miles away by altering the circulation of the atmosphere or by feeding moisture into larger weather systems. The storms of the tropics help drive the global circulation that brings rain to the middle latitudes. The storms of the middle latitudes help cool the tropics by transporting heat poleward. Every thunderstorm, no matter how small, plays a role in the great machine of the global atmosphere. To watch a thunderstorm is to watch a small but essential part of the planetary weather system at work. Deep within the heart of a thunderstorm, an invisible process is taking place. It is a process of separation and accumulation, of building tension and eventual release. This is the process of electrical charging, the mechanism that transforms an ordinary storm cloud into a lightning-generating machine. The electrical charge within a thunderstorm is a phenomenon of extraordinary complexity and power, and it is the source of one of nature's most spectacular displays. To understand this process is to understand one of the most fundamental aspects of the thunderstorm. The story of electrical charging in a thunderstorm begins with the simplest of actions: collisions. Inside the storm cloud, particles of all sizes are in constant motion, carried up and down by the powerful updrafts and downdrafts. These particles include tiny ice crystals, larger particles of graupel or soft hail, supercooled water droplets that remain liquid below freezing, and larger raindrops. As these particles move past each other, they collide. And with each collision, something remarkable happens. Charge is transferred from one particle to another. When an ice crystal collides with a graupel particle, electrons are transferred from one to the other. The direction of the transfer depends on the temperature of the particles. In the colder upper regions of the cloud, the lighter ice crystals tend to lose electrons and become positively charged. The heavier graupel particles tend to gain electrons and become negatively charged. This is a key point. The particles are not just bouncing off each other. They are exchanging charge, and the outcome of this exchange depends on the conditions within the cloud. The colder the temperature, the more pronounced this charge separation becomes. The reason for this charge transfer lies in the structure of the ice itself. Ice has a property called the thermoelectric effect, which means that different parts of an ice crystal can develop different electrical potentials depending on temperature. When two ice particles collide at the right temperature, one particle preferentially loses ions to the other. This process is subtle, but over billions of collisions, it produces a significant separation of charge within the cloud. The total charge that builds up in a thunderstorm can be enormous, enough to create potential differences of hundreds of millions of volts. Once the particles have exchanged charge, the updrafts and downdrafts take over the process. The updrafts carry the lighter, positively charged ice crystals upward toward the top of the cloud. The downdrafts carry the heavier, negatively charged graupel particles downward toward the middle and lower parts of the cloud. This gravitational separation is crucial. It ensures that the positive and negative charges are not uniformly mixed throughout the cloud, but are instead concentrated in different regions. The upper part of the cloud becomes a reservoir of positive charge, while the lower part becomes a reservoir of negative charge. The result is an electrical field within the cloud. The upper part of the cloud becomes positively charged, and the middle and lower parts become negatively charged. The electrical field between these regions can become extraordinarily strong, reaching hundreds of thousands of volts per meter. To put this in perspective, the electrical field in the air around us on a clear day is about 100 volts per meter. The electrical field within a thunderstorm is thousands of times stronger. This field exerts a force on every charged particle in the cloud, influencing their motion and their distribution. The negative charge at the bottom of the cloud also influences the ground below. The powerful negative charge repels electrons on the Earth's surface, pushing them deeper into the ground. This leaves the surface itself with a net positive charge. The ground beneath the storm becomes positively charged, creating another electrical field, this one between the cloud base and the Earth. The positive charge on the ground is not fixed in place. It moves with the storm, shifting as the cloud moves, a ghostly mirror of the charge above. The ground under a thunderstorm is alive with electrical activity, even before lightning strikes. As the storm builds and the charge separation increases, the electrical field reaches a point where the air can no longer insulate. Air is normally an excellent insulator, but under the stress of a sufficiently strong electrical field, it breaks down. Electrons are torn from air molecules, creating a plasma of charged particles. This ionized air becomes conductive, and a path begins to form through it. This path is the stepped leader, the forerunner of the lightning bolt. The breakdown of the air is a dramatic event, happening in a small fraction of a second. The stepped leader descends from the cloud in a series of rapid steps, each step advancing the leader closer to the ground. The leader follows the path of least resistance, which is determined by the distribution of charge in the air and the ground below. The leader branches as it descends, sending out tendrils that probe the air for the easiest path. This branching is what gives lightning its characteristic forked appearance. Each branch is a snapshot of the electrical field at that moment, a record of the path that the lightning chose. When the stepped leader reaches within about 100 feet of the ground, the positive charge on the surface is drawn upward. Streamers of positive charge rise from tall objects like trees, buildings. One of these streamers meets the descending leader, completing the circuit. In an instant, a massive current flows through the ionized channel, and the lightning flash is seen. This is the return stroke, the visible part of lightning that we see from the ground. The return stroke is incredibly bright, easily visible from many miles away. The return stroke carries a current of up to 200,000 amperes. To understand how much that is, the typical household circuit carries 15 or 20 amperes. A lightning bolt carries 10,000 times that much current. The power in a lightning bolt is immense, and it is delivered in a fraction of a second. This is why lightning can cause so much damage. It is not just the voltage, which can be hundreds of millions of volts, but the sheer quantity of current that flows. The energy released in a single lightning bolt is enough to light a home for several days. Not all lightning strikes the ground. Most lightning stays within the cloud, traveling between regions of opposite charge. Intra-cloud lightning is actually more common than cloud-to-ground lightning. It accounts for about 3/4 of all lightning flashes. Intra-cloud lightning is the flickering light that we see inside a storm cloud, illuminating it from within. It is just as powerful as cloud-to-ground lightning, but it is less dangerous because it does not reach the ground. The electrical activity within the cloud is constant during the mature stage of a storm, with many flashes occurring every minute. The electrical charge in a thunderstorm is not static. It is constantly being generated, separated, and discharged. The storm is a generator, converting the mechanical energy of the updrafts and downdrafts into electrical energy. This conversion is remarkably efficient. A single thunderstorm can produce enough lightning to power a small city, if only we could harness it. But the lightning is not the only product of the storm's electrical activity. The electrical field also affects the development of precipitation, the formation of hail, and the behavior of the storm itself. After the storm passes, the electrical charge dissipates. The clouds break apart, the electrical field weakens, and the lightning ceases. The atmosphere returns to its neutral state. But the process of charging and discharging has left its mark. The lightning has fixed nitrogen in the air, converting it into a form that plants can use. Each lightning bolt creates nitrogen oxides that are washed to the ground by rain, providing natural fertilizer for the soil. The electrical activity of thunderstorms plays a small but significant role in the global nitrogen cycle, connecting the power of lightning to the growth of plants. The storm's electrical legacy lives on in the fields and forests that benefit from its invisible gift. The electrical charge in a thunderstorm is a reminder that the atmosphere is an active, dynamic system. It is not just a passive layer of gas, but a place where energy is constantly being transformed. The mechanical energy of the updrafts becomes the electrical energy of the lightning, which becomes the light and heat of the flash, which becomes the sound of the thunder. This chain of energy transformation is one of the most remarkable features of the thunderstorm, a demonstration of how energy can change form while being conserved. There is also something deeply satisfying about understanding how the electrical charge in a thunderstorm works. The invisible process of charge separation, the building of the electrical field, the dramatic release of the lightning flash, all of it follows from simple physical principles. The storm is not magic, it is physics, and the physics is beautiful. The electrical charge in a thunderstorm is a testament to the elegance of the natural world, where collisions between tiny ice particles can lead to one of the most spectacular displays in all of nature. The storm is a laboratory, and the lightning is its experiment, conducted daily for anyone who cares to observe. Not all thunderstorm winds are equal. While the updraft is the engine that drives the storm, the downdraft is equally important. When the downdraft reaches the ground, it spreads out in all directions, creating winds that can be gentle or violent. The most intense downdrafts are called microbursts, and they are among the most dangerous phenomena associated with thunderstorms. Understanding microbursts and downdrafts is essential to understanding the full power of a storm and the many ways it can affect the world beneath it. A downdraft begins when precipitation within the cloud becomes too heavy for the updraft to support. Rain and hail begin to fall, dragging air down with them. This falling air is cooler than the surrounding air, both because it has been cooled by the evaporation of rain and because it originated at higher, colder altitudes. The cold, dense air accelerates downward, like a stone falling through water. The downdraft gains speed as it descends, and by the time it reaches the ground, it can be moving at a significant velocity. The downdraft is the storm's way of returning to Earth, of completing the cycle of rising and falling. When the downdraft hits the ground, it spreads outward in a radial pattern, like water from a faucet hitting a sink. This outflow of cool air is called a gust front. The gust front can extend for many miles ahead of the storm, and it is often felt as a sudden, cool breeze that signals the storm's approach. The leading edge of the gust front can lift warm, moist air, triggering new thunderstorm cells. This is how multi-cell storms maintain themselves, by using their own outflow to generate new growth. The gust front is a self-perpetuating mechanism that allows storms to last far longer than a single cell could. Most downdrafts are relatively gentle, producing winds of 20 to 30 miles per hour. These gentle downdrafts are simply the cool outflow that accompanies a passing shower. They are refreshing on a hot day and cause no damage. But some downdrafts are much stronger. When a downdraft is particularly intense and covers an area of less than 2.5 miles, it is called a microburst. Microbursts can produce winds of up to 150 miles per hour, equivalent to a moderate tornado. But unlike tornadoes, which are rotating, microburst winds are straight-line winds that radiate outward from a central point. Microbursts are classified into two types, wet and dry. Wet microbursts occur in conditions of high humidity. They are accompanied by heavy rain, and they are common in the southeastern United States and in tropical regions. The rain is visible as a shaft descending from the cloud base, and the microburst is often associated with a dramatic wall of rain approaching. Dry microbursts occur in conditions of low humidity. The rain evaporates before it reaches the ground, but the downdraft itself continues to the surface. Dry microbursts are common in the western United States, particularly in the arid regions of the Southwest. They are especially dangerous because they can occur with little visible warning, under a cloud that may not look particularly threatening. The danger of microbursts lies in their suddenness and intensity. A microburst can develop in minutes and reach its peak intensity in seconds. The wind speeds can be extreme, and the direction of the wind changes rapidly as the outflow spreads outward. For aircraft, microbursts are particularly dangerous. A plane taking off or landing can encounter a headwind that suddenly changes to a tailwind, causing a loss of lift and a rapid descent. Microbursts have been responsible for several major aviation accidents, which is why they are studied so intensively by meteorologists and aviation safety experts. Modern aircraft are equipped with predictive wind shear detection systems that can warn pilots of microburst activity. The structure of a microburst is complex. The descending column of air hits the ground and spreads out, but the outflow is not uniform. The strongest winds are usually found near the center of the microburst, where the downdraft is most intense. The winds decrease with distance from the center, but they can still be dangerous far from the point of impact. The outflow can also be channeled by terrain, with buildings and hills creating eddies and zones of accelerated flow. The wind pattern within a microburst can be highly variable, making it difficult to predict exactly where the strongest winds will occur. Microbursts can cause significant damage on the ground. They can knock down trees, damage roofs, overturn vehicles, and level structures. The damage pattern from a microburst is distinctive. Unlike a tornado, which leaves a narrow, twisting path of destruction, a microburst leaves a radial pattern, with debris pointing outward from a central point. This pattern helps damage surveyors distinguish between tornado damage and microburst damage. The debris from a microburst is often scattered in all directions, like spokes on a wheel, rather than following a single narrow path. There is also a larger version of the microburst called the macroburst. A macroburst covers an area larger than 2.5 miles in diameter, and it can produce winds of up to 100 miles per hour. Macrobursts last longer than microbursts, typically 5 to 30 minutes, and they can affect a much larger area. Both microbursts and macrobursts are forms of what meteorologists call downbursts, any strong downdraft that causes damaging winds at the surface. Downbursts are a common type of severe weather, and they are responsible for a significant portion of thunderstorm damage. The formation of a microburst is closely tied to the presence of dry air at mid-levels of the atmosphere. When rain falls from the cloud into this dry air, it evaporates rapidly. Evaporation is a cooling process, and the rapid evaporation cools the air significantly. This cooled air is much denser than the surrounding air, and it accelerates downward. The process feeds on itself. The faster the air descends, the more rain it carries, and the more evaporation occurs. This feedback loop can produce extremely rapid acceleration of the downdraft, resulting in the intense winds of a microburst. Meteorologists use Doppler radar to detect microbursts. The radar can measure the speed and direction of the winds within the storm, and it can detect the characteristic signature of a microburst, a small area of intense downward motion followed by a divergence of winds at the surface. When a microburst is detected, warnings can be issued, giving people time to take cover. Aviation weather systems use automated algorithms to detect microbursts and alert pilots and air traffic controllers. These systems have greatly improved aviation safety since their introduction. Despite their power, microbursts are short-lived. A typical microburst lasts only 5 to 15 minutes from the time it reaches the ground to the time it dissipates. The downdraft weakens as it spreads out, and the outflow merges with the surrounding air. In the aftermath of a microburst, the air is calm again, and the damage is left as the only evidence of what happened. The brevity of microbursts makes them particularly challenging to forecast and detect, but advances in radar technology have greatly improved our ability to identify them and warn those in their path. Downdrafts and microbursts are a reminder that a thunderstorm's energy is not contained entirely within the cloud. The storm reaches down to the surface, touching the ground with wind and rain. The interaction between the storm and the ground is complex, shaping the storm's evolution and creating the weather that we experience. The downdraft is the storm's way of returning to Earth, of completing the cycle of rising and falling that defines the thunderstorm. And in its most intense form, the downdraft becomes a microburst, a concentrated burst of power that demonstrates in a few brief minutes the full force of the atmosphere. These winds, though brief, are among the most powerful and dangerous expressions of the storm's energy. The study of microbursts and downdrafts has practical benefits beyond aviation safety. Understanding how downdrafts work helps engineers design buildings that can withstand strong winds. It helps city planners make decisions about where to locate critical infrastructure. It helps farmers understand how storm winds can damage crops. The knowledge gained from studying these phenomena has applications in many fields, and it continues to grow as our observing technology improves. There is also a lesson in humility to be found in microbursts. They remind us that the atmosphere can produce forces far beyond anything we can create. A microburst can generate winds as strong as a tornado, but it does so in a way that is entirely different through the simple mechanism of cold air sinking. The power of the microburst is the power of gravity, of density differences, of the basic physics of the atmosphere. It is a reminder that the most powerful forces in nature are often the simplest ones, and that we ignore them at our peril. The downdraft is the storm's quiet counterpoint to the dramatic updraft, and in its most intense form, it is just as worthy of our respect. Thunderstorms have been a part of human experience since the beginning of our species. Before we understood the science behind them, we wove stories around them. We gave them meaning and power. We saw in them the work of gods and spirits, the expression of forces beyond our control. The history of human interaction with thunderstorms is as rich and varied as the cultures that have experienced them, and it reveals much about how we have tried to understand the natural world. The storm has always been a mirror for our beliefs and our imagination. In ancient Greek mythology, thunderstorms were the domain of Zeus, the king of the gods. Zeus wielded the thunderbolt as his weapon, and he used it to assert his authority over both gods and mortals. When a storm raged across the sky, the Greeks believed that Zeus was throwing thunderbolts, expressing his power and his anger. The thunderbolt was a symbol of divine authority, and it appeared on coins, in art, and in literature throughout the Greek world. The Romans had a similar figure in Jupiter, who also controlled thunder and lightning. The very word jovial comes from Jupiter, reflecting the idea that the king of the gods could be both terrible and benign. The Norse peoples had Thor, the god of thunder, who rode across the sky in a chariot drawn by goats. The sound of thunder was the sound of Thor's chariot wheels, and lightning was the flash of his hammer, Mjolnir, as he struck his enemies. Thor was a protector of humanity, and his thunder and lightning were forces that defended the world of humans against the giants and monsters that threatened it. Thursday, Thor's Day, is named after him, a lasting reminder of the importance of the thunder god in Norse culture. The story of Thor has survived into modern times, appearing in comics, movies, and popular culture. In Hindu mythology, Indra is the god of thunder, lightning, and rain. He wields the thunderbolt Vajra, a weapon made from the bones of a sage, and he uses it to defeat demons and bring rain to the parched earth. Indra is a king of the gods in the early Vedic tradition, and his association with storms and rain made him one of the most important deities in the pantheon. The monsoon storms that sweep across India were seen as Indra's work, a yearly renewal of the earth's fertility. The people would pray to Indra for the right amount of rain, not too little and not too much. In many Native American traditions, thunderstorms were seen as powerful spirits. The thunderbird, a giant bird whose wings made the sound of thunder and whose eyes flashed lightning, is a common figure in the mythology of many tribes. The thunderbird was a creature of immense power, capable of both destruction and renewal. In some traditions, the thunderbird fought against the water spirits in the underworld, maintaining the balance of the world. The thunderbird remains an important symbol in many Native American cultures today, appearing in art, dance, and storytelling. In Chinese mythology, thunderstorms were associated with the dragon. The dragon was a bringer of rain, and its movements through the sky were accompanied by thunder and lightning. Dragons were respected and feared, and they were often depicted in art and literature as the masters of the weather. The Chinese believed that thunderstorms were the dragons at play, and they offered prayers and sacrifices to ensure that the dragons would bring the right amount of rain for the crops. The dragon dance, performed during festivals, is a remnant of these ancient beliefs. In Japan, thunder and lightning are associated with Raijin, the god of thunder, and Fujin, the god of wind. Raijin is often depicted as a fearsome demon beating drums to create the sound of thunder. Lightning was believed to be caused by Raijin's drumsticks or by the claws of his companion, Raiju, a mythical creature that would descend to earth during thunderstorms. The Japanese tradition of avoiding certain activities during thunderstorms has its roots in these ancient beliefs. Raijin and Fujin are still depicted in Japanese temples and art, enduring symbols of the power of the storm. The Bible contains numerous references to thunderstorms as expressions of divine power. In the book of Job, God speaks to Job out of a storm, using the thunder and lightning as a demonstration of his authority over creation. The storm is a symbol of God's power, something that humans cannot control or fully understand. This theme appears throughout the Old Testament, where storms are often associated with divine presence and judgment. The rainbow after the storm, a sign of God's covenant with Noah, is one of the most enduring symbols of hope in Western culture. In more recent history, thunderstorms have played a role in literature, art, and music. The Romantic poets of the 19th century were fascinated by storms. They saw in them a reflection of human emotion, the sublime power of nature that inspired both awe and terror. The painter J.M.W. Turner captured the drama of storms in his paintings, using light and color to convey the intensity of the weather. In music, composers like Beethoven and Wagner used thunder and lightning to create dramatic effect. Beethoven's Pastoral Symphony includes a famous storm movement that captures the full arc of a storm, from its first stirrings to its peaceful aftermath. The scientific study of thunderstorms began in earnest in the 18th century with Benjamin Franklin's famous kite experiment. Franklin flew a kite into a thunderstorm and drew electricity from the air, proving that lightning was a form of electrical discharge. This experiment was incredibly dangerous, and Franklin was lucky to survive it. But it marked the beginning of our modern understanding of thunderstorms. Franklin's work led to the invention of the lightning rod, which has saved countless buildings from lightning damage. The lightning rod was one of the first practical applications of scientific knowledge about storms. In the centuries since Franklin, our understanding of thunderstorms has grown enormously. We now have radar that can see inside storms, satellites that can track them from space, and computer models that can predict their behavior. We can warn people hours in advance that a severe storm is approaching. But for all our scientific knowledge, thunderstorms still retain a sense of mystery and power. They are still capable of inspiring awe, of making us feel small in the face of nature. The ancient myths and stories that humans told about thunderstorms are not entirely gone. They live on in our language, in our art, and in the way we speak about the weather. The cultural history of thunderstorms reminds us that our relationship with nature is not purely scientific. It is also emotional, spiritual, and creative. We approach thunderstorms with a mixture of fear and fascination, of respect and wonder. We have always done so, from the earliest humans who huddled in caves during storms, to the modern meteorologists who track them with sophisticated instruments. The storm is both a physical phenomenon and a cultural symbol, a reminder of the power of nature and the creativity of the human spirit in responding to it. The stories we tell about storms are stories about ourselves. Thunderstorms have also left their mark on our language. We speak of stormy relationships, of lightning-fast decisions, of thunderous applause. The vocabulary of storms has become the vocabulary of human emotion and experience. When we say that someone has a stormy temperament, we are drawing on thousands of years of cultural association between storms and powerful emotion. When we describe a decision as lightning fast, we are invoking the speed and suddenness of the lightning bolt. The language of storms is woven into the fabric of how we speak, a constant reminder of the influence of weather on our lives. The cultural history of thunderstorms is a reminder that our relationship with nature is not purely rational. We do not approach thunderstorms as computers would, simply calculating probabilities and risks. We approach them as humans, with a mixture of fear and fascination, of respect and wonder. We tell stories about them because stories help us make sense of the world. The stories may have changed over the centuries, from myths about gods to scientific explanations about charge separation, but the impulse behind them is the same. We want to understand the storm. We want to find our place in relation to it. And in the end, the stories we tell about storms tell us as much about ourselves as they do about the weather. The legacy of thunderstorms in human culture is a testament to the power of nature to inspire us. Whether through the myths of the ancients, the art of the Romantics, or the science of the modern era, thunderstorms have pushed us to think, to create, and to understand. They have given us gods and heroes, paintings and symphonies, lightning rods and weather radar. They have been a constant presence in the human story, a source of fear and wonder, of destruction and renewal. And they will continue to be so for as long as there are humans to look up at the sky and marvel at the power of the storm. There is a particular kind of pleasure that comes from watching a thunderstorm from a safe place. It is a feeling of being sheltered, of being protected while the storm rages outside. This feeling is one of the great gifts of thunderstorms, the opportunity to experience the power of nature without being exposed to its dangers. Watching a storm from safety is an experience that we have enjoyed for as long as we have had buildings to shelter us, and it is one that never grows old. It is a simple pleasure, but a deep one. The best place to watch a thunderstorm is from a sturdy building with a view of the sky. A window that faces the direction of the approaching storm offers a front row seat to the drama unfolding outside. As the storm approaches, the sky darkens, the clouds build, and the first flashes of lightning appear on the horizon. The storm is still far away at this point, and the thunder takes many seconds to arrive. The space between the flash and the thunder slowly shrinks as the storm draws nearer, a gentle countdown to the storm's arrival. The anticipation builds with each flash. There is a meditative quality to watching a storm approach. The storm moves at its own pace, unhurried and inevitable. The clouds roll in, layer upon layer, each one darker than the last. The light changes, shifting from bright sunlight to a dim greenish twilight. The wind picks up and the trees outside begin to sway. The first raindrops hit the window and the storm begins in earnest. Each phase of the storm's approach has its own beauty, and watching it unfold is a lesson in patience and observation. There is nothing to do but watch, and that is exactly the point. The sound of the storm is part of the experience. From inside a building, the thunder is muffled, softened by the walls and the roof. The rain on the roof creates a steady, rhythmic sound that fills the room. The wind howls around the corners of the building, but inside, there is only the sound of the storm filtered through the structure. There is a comfortable distance between the observer and the storm, a sense of being in a bubble of safety while the weather rages outside. The sounds of the storm become background music, a natural soundtrack for the act of watching. Watching a thunderstorm at night has a special quality. The darkness makes the lightning more visible, and each flash illuminates the sky like a celestial camera flash. The clouds are outlined in silver and gold, and the world outside is frozen for a split second before returning to darkness. The thunder seems louder at night, perhaps because the darkness removes visual distractions and makes us more attuned to sound. The night storm is a light show, a display of nature's power that needs no music or narration. The lightning creates patterns in the darkness, each flash unique and unrepeatable. The rhythm of a thunderstorm is part of its appeal. There is a natural ebb and flow to the storm, with periods of intense activity followed by periods of relative calm. The rain comes in waves, heavy and then light, heavy and then light. The thunder follows a similar pattern with close strikes that shake the building and distant rumbles that fade into the background. This rhythm is soothing, a natural pulse that the body responds to. It is no wonder that so many people find the sound of a thunderstorm relaxing enough to sleep to. The storm provides a natural lullaby. For many people, the best way to watch a storm is from a porch or a covered patio, where the rain is just out of reach. The sound of the rain is different here, sharper and more immediate. The smell of the wet earth and the clean air fills the space. The cool breeze carries the mist of the rain. Being under a roof but still outside offers a different kind of connection to the storm, a sense of being on the edge of the weather rather than fully enclosed by it. The boundaries between inside and outside blur, and the observer feels closer to the storm while still being protected. Thunderstorms offer a rare opportunity to disconnect from the modern world. During a severe storm, it is common to lose power, and the resulting darkness and silence force us to slow down. Without the constant hum of electronics, the storm becomes the only entertainment. The lightning provides the light, the thunder provides the sound, and the rain provides the soundtrack. In these moments, we are reminded of a simpler way of being, one that is more connected to the natural rhythms of the world. The storm strips away the distractions and leaves us with the essentials. Watching a storm can also be a social experience. Families gather at windows to watch the lightning together. Friends text each other to ask if they saw that last flash. The storm becomes a shared event, something that brings people together. There is a sense of community in weathering a storm together, even if the weathering is just watching from the safety of our homes. The storm reminds us that we are all in the same weather, subject to the same forces, sharing the same sky. It is a rare moment of collective attention in a world that is often fragmented. For those who want a deeper experience, keeping a storm journal can be a rewarding practice. Noting the time the storm began, the direction it came from, the frequency of lightning, and the duration of the rain can create a record of the storms that pass through a particular place. Over time, patterns emerge. Some directions bring more storms. Some seasons are more active. The journal becomes a personal history of the weather, a record of the sky's moods. It also deepens the observation, turning passive watching into active attention. The art of watching storms is not complicated. It requires only a safe place, a clear view, and a willingness to be present. The storm will do the rest. It will provide the drama, the sound, the light, and the movement. The watcher's role is simply to observe, to take it in, to let the storm wash over the senses. In a world that is always busy, always demanding attention, the thunderstorm offers a rare gift, a reason to stop and look up, to pay attention to something larger than ourselves. The storm asks nothing of us but our attention, and that attention is rewarded with beauty. When the storm passes and the sky begins to clear, there is a moment of transition. The rain stops, the thunder fades, and the wind dies down. The clouds break apart, and the first rays of sunlight break through. The world outside is wet and fresh, washed clean by the rain. The watcher has witnessed the entire arc of the storm, from its approach to its climax to its departure. It is a complete experience, one that leaves a sense of satisfaction and calm. The storm has come and gone, and the watcher was there to see it all. The memory of the storm lingers, a reminder of the beauty that can be found in simply paying attention. Watching a thunderstorm is an act of mindfulness. It requires nothing but presence. There is no task to complete, no goal to achieve, no problem to solve. The only requirement is to be there, to watch, to listen, to feel. In a world that constantly demands our attention and our productivity, the thunderstorm offers a rare permission to simply be. The storm does not care about our to-do lists or our obligations. It proceeds at its own pace, indifferent to our schedules, and in doing so, it invites us to slow down and join it. The pleasure of watching a storm is also the pleasure of perspective. The storm is large, powerful, and indifferent. It does not know that we are watching it. It does not care, and yet, in watching it, we are reminded of our place in the world. We are small, and the storm is large, and that is not a frightening thought, but a comforting one. It is a relief to be reminded that the world is bigger than our worries, that there are forces at work that have nothing to do with our daily concerns. The storm puts our problems in perspective, shrinking them down to their proper size. In the face of the thunderstorm, the small things become small again, and we are free to let them go. There is also a social dimension to watching storms. In the age of smartphones, Watching a storm has become a shared digital experience as well as a physical one. People post photos and videos of storms, sharing their experiences with friends and strangers alike. The storm becomes a topic of conversation, a moment of collective attention in a world where attention is increasingly fragmented. The storm brings people together, both physically and virtually, creating a sense of community around a shared experience. Even if we watch the storm alone, we know that others are watching it too, and that knowledge connects us. The storm has passed. The thunder fades to a distant murmur, and the last flashes of lightning flicker on the horizon. The rain slows from a downpour to a shower, then to a drizzle, then to nothing at all. The wind, which had been howling, settles into a gentle breeze. The storm is moving on, leaving behind a world that has been washed and renewed. This is the peace after the storm, a moment of stillness that follows the drama of the weather. It is a moment that has been anticipated since the first drops of rain fell. The first thing that becomes apparent is the quiet. After the noise of the storm, the silence is striking. The rain on the roof, the thunder in the sky, the wind in the trees, all of these sounds stop, and what remains is a deep, profound quiet. It is not an absolute silence. The sounds of dripping water and of birds beginning to sing again fill the air. But compared to the storm, it is the quietest of quiet, a silence that feels like a gift after the noise. The transition from the noise of the storm to the peace of its aftermath is one of the most satisfying experiences in nature. The air after a storm is different. It is cleaner, fresher, cooler. The rain has washed the dust and pollen out of the air, leaving it clear and crisp. The temperature has dropped and the humidity feels lower. The air has a quality that is hard to describe, but easy to recognize, a feeling of lightness and clarity. Breathing this air is a pleasure, each breath carrying the scent of wet earth, of wet leaves, of the rain itself. The air feels alive, charged with the energy of the storm that has just passed. The smell after a thunderstorm is one of the most distinctive scents in nature. It is called petrichor, a word derived from the Greek words for stone and the fluid that flows in the veins of the gods. Petrichor is the smell that comes when rain falls on dry ground, and it is caused by a combination of plant oils and a compound called geosmin, which is produced by bacteria in the soil. The rain releases these compounds into the air, creating the fresh, earthy scent that fills the world after a storm. The smell of petrichor is one of the most universally loved scents in nature. The landscape after a storm is transformed. The rain has saturated the ground, and puddles of clear water reflect the sky. The leaves of trees and plants are coated with water droplets, each one catching the light like a tiny jewel. The colors of the world seem more vivid after a storm. The green of the leaves is deeper, the brown of the bark is richer, the blue of the sky is more intense. The rain has cleaned everything, and the world looks as if it has been polished. Every surface gleams with the moisture left behind by the storm. The light after a storm has a special quality. The storm clouds are breaking up, and the sun is breaking through the gaps. The sunlight is low and golden, casting long shadows and creating a warm glow. Against the retreating storm clouds, the light can create spectacular effects, with beams of sunlight streaming through the clouds in what are called crepuscular rays. The clouds themselves take on colors, with pinks and oranges and purples painting the retreating storm. The light after a storm is some of the most beautiful light that nature produces. For those who step outside after a storm, the experience is one of renewal. The ground is soft underfoot, and the air is cool on the skin. The world is quiet and still, as if it is recovering from the energy of the storm. The sound of dripping water is everywhere, a gentle percussion that accompanies the silence. The birds begin to emerge, cautiously at first, then with more confidence, their songs filling the air. The birds know that the storm has passed, and they sing their relief. The world is coming back to life after the pause of the storm. The storm has done more than just clean the air and water the ground. It has also changed the atmosphere in a deeper sense. The electrical activity of the storm has produced nitrogen compounds that are carried to the ground by the rain, providing natural fertilizer for the soil. The rain has replenished the water table, filling streams and reservoirs. The wind has scattered seeds and pollen, helping plants to reproduce. The storm has done its work, and the world is better for it. The storm is not just a destructive force, it is also a renewing one, essential to the health of the ecosystem. There is a lesson in the aftermath of a thunderstorm. The storm is a reminder that the most intense experiences, the ones that shake us and challenge us, do not last forever. They pass, and what comes after is a sense of peace and renewal. The storm breaks, and the sun comes out. The thunder roars, and then there is silence. The world is washed clean, and we are given a chance to start again. This pattern of turmoil followed by calm is one of the fundamental rhythms of life. The storm teaches us that every difficult passage eventually gives way to peace. The peace after the storm is a time for reflection. The storm has come and gone, and we have weathered it. We have watched it from safety, and now we walk out into the world it has left behind. The puddles reflect the sky, the birds are singing, and the air is fresh. The storm has passed, and we are still here. There is a sense of accomplishment in this, a feeling of having witnessed something powerful and having come through it unharmed. The peace that follows is earned, a reward for having been patient and staying safe. As the last clouds drift away and the sky clears fully, the sun warms the wet ground and steam begins to rise. The world is slowly drying out, returning to its normal state. The storm becomes a memory, a story to tell, a moment in the ongoing cycle of weather. But the peace it leaves behind lingers. The air stays clear, the ground stays soft, and the quiet persists for a while longer. A gift from the storm to those who were patient enough to wait for it. The peace is a reminder that every storm eventually ends. The peace after the storm is not just the absence of noise, it is a positive presence, a feeling of calm that settles over the world. It is the world catching its breath, taking a moment of rest before the next system moves in. It is the quiet that follows a good cry, the stillness after a hard rain, the silence that comes when nature has finished its work. It is a reminder that every storm eventually ends, and that what follows is worth waiting for. The storm has passed, and the world is at peace. The air is fresh, the sky is clear, and the earth is renewed, ready for whatever comes next. The peace after the storm is not permanent, of course. The atmosphere is always in motion, and another storm will eventually come. But that is not a reason to diminish the peace of this moment. The calm after the storm is real and valuable, even if it is temporary. It is a pause in the ongoing rhythm of the weather, a breath between the notes of the atmospheric symphony. And like all pauses, it gives meaning to what came before and what will come after. There is a lesson in the peace after the storm about the nature of change. The storm seemed permanent when it was raging, but it was not. It passed, as all storms do. The peace that followed seemed fragile, but it was not. It was solid and real, a genuine stillness that settled over the world. The impermanence of both the storm and the peace is not a cause for sadness, but a reason for gratitude. The storm was powerful, and we witnessed it. The peace is quiet, and we are experiencing it. Both are gifts, and both deserve our full attention. To sit in the peace after a storm is to understand something essential about life. After every storm, no matter how intense, there is calm. After every difficulty, no matter how overwhelming, there is rest. The storm does not last forever. The thunder eventually fades, the rain eventually stops, and the sun eventually returns. The peace after the storm is not just a meteorological event. It is a promise, written into the fabric of the natural world, that no storm is final. The peace always comes if we are patient enough to wait for it. As our story slowly comes to an end, allow the final thoughts to fade, gently into the quiet of the night. The rain and the calm ideas and the peaceful moments we've explored can settle softly in the background like distant echoes of a quiet evening. There is no need to think about anything now. Your body can continue to relax, breathing slow and steady. If you are still awake, simply remain here a little longer and enjoy the calm atmosphere. And if sleep has already started to find you, let it arrive naturally and without effort. Thank you for spending this quiet moment here on Cozy Sleep Time. If you enjoy these calm stories and gentle explorations, you can return anytime for another peaceful journey into rest. For now, let the night grow quieter and quieter and quieter, and allow yourself to drift deeper into sleep. Good night.